mostly talking about the moon tonight and how lunar samples connect the present, the past, and the future. And just like you can see from these images here, this is a map of the moon that Galileo drew in 1610, and then 70 years later, Cassini with remarkable detail. And here you can see what our images of the moon today look like. Just like our observation skills have evolved with time, so have our views of the moon and how it evolved over time. And so we're going to talk about that a little bit, about Apollo, about ANGSA, the present, and then Artemis, just a teeny tiny bit, which is coming up in the future. All right, so before we go into the nitty-gritty bits, like why do we care about the moon? Why should you all care about the moon? And not just because it looks pretty in the sky, but just in general, all the things we can learn from it. So ever since humans have evolved and have looked up into the night sky, we have started asking questions. Where do we come from? How did Earth form? Where's all the water coming from? How old is the Earth? What were the building blocks that made our planet? How did the solar system form? How old is the solar system and where do we come from, right? And you would think because we're living on a planet that we could just walk around, pick up rocks, because that's obviously what geologists do, or part of what we do. We could learn a lot or answer some of these questions that we have about our own planet and the history of our planet and maybe the history of our solar system, right? Well, the problem with our planet, and you can sort of see here, is that it's very active. We have plate tectonics, you can see here, where material gets brought back into the interior of our planet, where it gets melted, and then it gets brought back up to the surface through volcanism, where maybe we have some degassing going on. We have rain and wind and snow, so we have weathering processes going on that will, over time, abrade the rocks, turn them into soil and sediments, transport them back into the oceans, where then eventually everything gets back introduced into the interior, it gets mixed and melted. And so Earth is a gigantic recycling machine. And all the old geologic evidence that we could have used to answer some of these questions, or most of these questions, all of this evidence has been destroyed and turned into something new and basically reset. So if we want to learn something about the history of our own planet, the history of our solar system, we have to find a place that hasn't changed much since its formation, and then look at the rocks from that particular place. And it happens to be the moon, which is our closest neighboring planetary body. It's only 3-ish days away, so it's not that far, right? And it hasn't really changed much since its formation. And because it has preserved all these records of planetary formation and early history, we can call it a museum of planetary history. It has been interacting also with the solar wind and the galactic race, and therefore it's also a space probe and a time machine, because by looking at these rocks that have been interacting for so many billions of years, they sort of represent an archive of the solar system climate. For example, how the sun output has changed over time, what kind of materials were around very early on that impacted the moon. All of this has been preserved. And so all we really need to do as planetary scientists or lunar scientists is to learn how to read this archive, how to take the rocks from the surface, the soil, the regolith, and interpret this archive, and then learn everything we want about the solar system and the Earth-Moon history. And so I'm going to talk to you a little bit about stuff that we have recently found, some really interesting, cool new things, and there will be lots and lots of pretty pictures. So this is our past, right? Apollo in 1969, we went to the moon for the very first time. Okay, I'm going to make you feel a teeny tiny bit old. Who has actually seen the original Apollo 11 landing? All right, I'm a tiny bit jealous, so you know. Maybe I'm a little bit jealous. I'm sure that was absolutely super amazing, right? And so this is actually one of my favorite images from Apollo 17, 1972, the last mission. And I love this image so much because you can see the tire tracks of the lunar vehicle that they used to drive around on the surface and go around and collect all these amazing samples. And I also really like it because that's where the Apollo drill core comes from that we're going to talk about a little bit later. Right, so overall, the astronauts brought back 382 kilograms of rocks. And so This is really exciting from our past. This is going to be our future, Artemis 2024, where we hopefully land the next humans on the moon, including women. So I'm super excited about that, obviously. And we're going to go to the South Pole. So that's very, very different from the Apollo landings that were on the near side. And we're going to hopefully use that mission to learn something about what resources are available to us on the moon, how we can use this for maybe long-term space exploration, and then how we can use the moon as a stepping stone to get to Mars. All right, so let's talk about the present a little bit. We have the ANGSA program, which stands for Apollo Next Generation Sample Analysis Program. And all the Apollo rocks are stored in the Pristine Lunar Sample Vault, including some of the Apollo samples that haven't been opened, which is what this program is about. So when the Apollo samples got brought back, NASA had the foresight to be just like we saw how the pictures evolved in our observation skills. They thought, well, our technologies will evolve over time, so let's not open all the Apollo samples at the same time, because maybe there are scientific questions out there that we don't even know how to ask them yet. And maybe our technology will evolve so we can study them better in the future. So because they had this foresight, they kept some of the samples stored away and never opened them. And now 50 years later, after Apollo 11 anniversary, it's time to at least open some of them. And so the Apollo 17 drill core is being opened right now. And so here is where all the samples are being stored. This is the size or the thickness of the vault door. There is a Brian for scale. This is Charisse, one of our processors, and Jeremy. It's really heavy to actually lift this door open. You can see how Charisse is leaning in to pop it open. And then if you look through this door, this is what you see on the inside. This is where all the Apollo samples are now being stored. And you can see everybody dresses up in these bunny suits. Here's Charisse again. This is Andrea. These are our two superstars. And these are also superstars here. These are our other processors. And so these people help us process the samples. Each cabinet is for a specific mission. So for Apollo 11, for Apollo 16. And inside the cabinets is nitrogen gas. They have gloves on the outside. They're all covered up here, but in this image here, you can see Ryan take the covers off, and you can see the gloves kind of popping out because there's positive pressure on the inside so that nothing ever can leak inside the samples. And we're doing this because we want to protect the samples from us, right? Earth is kind of dirty and germy, and I don't know. So we want to make sure that the Apollo samples are staying pristine as much as they can. So in this sample vault, there's a very special glove box. You can see here. It has very special covers for the gloves. And it has a super security system right here. And if you zoom in to this area here, so this says core area. You must have an escort to enter this area. Right? Now, if you look into the glove box right there, you can see these samples here. So these are the unopened Apollo samples. They're still triple bagged and stored in this special glove box right there. So we took the Apollo 17 drill core out right here. Here you can see me with the actual drill core transferring the sample from the vault to the core processing lab. You can see from my facial expression, I'm super excited and extremely terrified at the same time, right? I was thinking, oh my God, if I trip and drop this, we're done. I can just pack up my stuff and be like, am I going to wait until they fire me, or am I just going to go? Right? So I've never in my life carried anything this carefully and this slowly from one room to the other. But we managed to get it over with nothing happened. And this is the area where we brought it to. This is the core processing area. This is the glove box here. You can see a lot of equipment up there. We had cameras and stuff up there so that people can actually see it. Here is the airlock where we transfer samples in. And if you look into the box, this is sort of what it looks like. There's a lot of equipment in here. This is part of the core where we use the extruder to push it out onto this little cart here. And this is where the core basically gets pushed out. This happened during the extrusion. This is the core, the Apollo 17 core team. There's Andrea. This is, whoa, Charisse. That was not me. Okay, let's see. What do I do? Nope. Or I can see it right here. It's not my clicker. Guy is working on it, don't worry. So there was the nice pretty picture. There you go. Yes. So first of all, yay women scientists, right? This is Cherise. She's the lead in our team. And here's Andrea. And here's myself. And so we got to actually open the actual sample and extrude it. And this is during the actual process. So we were in a room that had a glass window, so people on the outside could be there and sort of witness what we were doing without actually getting in our way and disturbing us, right? And so here's Cherise looking up. I'm reading off some numbers, I think, and Andrea is very critically observing that we're doing everything right. We had procedures that we followed that were laid out before. Here you can see the viewing area where people could actually see us. We're doing something here. I don't know, we're critically assessing something. The whole 2 days that we did this are kind of like a blur right now because we were very focused, and then at the end we just collapsed. And so everything is sort of like washed out a little bit. But we were doing something. And then this is the moment after we actually successfully extruded the core, and you can see we are ecstatic and relieved and tired and super happy all at the same time. So it was a super, super exciting experience, and working with Cherise and Andrea was absolutely beautiful and wonderful. So I'm really happy that I got to be part of this team. And this is what the core looked like right after we pushed it out. This is the top, so this is the surface of the moon, and this is going down into the surface. So this is 18.5 centimeters below the lunar surface. You can see how smooth this is because we pushed it into a glass top and a receptacle down here. So the first millimeter or so of the core got sort of mixed up. You can see that there's some void spaces here, and you can even see some mineral or clast fragments right there. So this mixture of the core, we wanted to remove. This is what we call a rind. So we want to de-rind the core so that we can see what is underneath, the stuff that hasn't been disturbed by just pushing it out. And you can see that the color varies here. This is a little bit darker right here. There's some white areas here. And so this was the beginning of the de-rinding process. And this is what it looked like when it was completely de-rinded, when we removed this mixed layer on the outside. And then the whole dissection process started. And that means we're taking every ½ centimeter of the core apart, and we put it in a sample, and then scientists can request to work on that. And so as Andy has already hinted, we have some members of the science team from ANGSA here at the moment. So here's again Cherise and Andrea and myself as the core team. And then here is Barbara Cohen, Dr. Barbara Cohen from NASA Goddard, Francesca McDonald from ESA, the European Space Agency, and then here Dr. Carrie Corrigan from the Smithsonian. So yay, women scientists again, just pointing this out. So we're a powerhouse right now. There's a lot of energy and happiness and jokes and really, really cool science going on right now. So what have we learned from these Apollo samples by looking at them? Well, we have learned, despite some very strong beliefs, that the moon is not made from cheese. It, in fact, is a differentiated igneous object. That means it is sort of like a planetary object that has a core, mantle, and a crust. And so what we think happened is that the moon was once covered in a global magma ocean, and all the minerals that crystallized from this magma ocean, the ones that were denser, sank towards the center and made the core and the crust, core and the mantle. And the really light minerals sort of floated towards the surface and made the crust. And these light minerals are called plagioclase, or the scientific term is anorthite. And so the rocks that the crust is made from is called anorthosite. And you can see it's actually white because the minerals are white, right? And so this is the very, very ancient early crust. And then over time, we all know the moon has been bombarded for millions and billions of years. So the surface has been broken up, and glued back together, and broken up again into pieces, and then mixed, and then glued back together. And so over time, the surface has been turned into a rock type that we call breccia. And so here is a typical Apollo breccia. You can see the different rock types and rock pieces all stuck together here into one now resolidated rock. And then eventually some of the larger impacts, we had some decompression melting and some other melting going on the moon, and then the melt found its way up through the cracks and filled the craters and crystallized to form basalt. And basalt happens to be black rock, just like our ocean floors are made from basalt, or Hawaii, right? You've all seen pictures from Hawaiian rocks, they're very black. So lunar basalts are also black. And so if you look into the night sky, you can still see the big craters, the big basins that have been filled with this melt that then crystallized to form basalt. And the ancient crust here you can see how bright it is. That's because the anorthosites and a lot of the breccias are white from these plagioclase grains. Okay, so most or all of lunar science is actually anchored through these Apollo samples. We need these samples to calibrate our spacecraft that go around the moon, that look at the reflected light from the surface that we use for remote sensing, and we can make these big maps of the moon of the albedo or chemical distribution. And we need to calibrate these, and best to do that is on actual moon rocks. And so that's what we're doing with the Apollo samples. We can also age date these rocks, and we can give it an absolute date. And because we know exactly where on the surface these rocks came from, we can now pinpoint a crater, and we can give that particular crater an absolute age. And so with that, we can then extend basically a timeline or an age of the surfaces. Before, we had a method we still have, it's called crater counting, where you could get kind of like a guesstimate of the age. So something that had lots of craters was obviously very old, and something that has no craters is very young, and you can see what is at the bottom, and then if something impacts it on top, clearly must be younger, and then that gets impacted as even younger. So you sort of like got a relative age of a surface. But now, having these rocks and knowing from which crater they come from, we can pinpoint and actually give it an absolute age. So that helps us with calibrating our age scales for not only the moon, but maybe also throughout the entire solar system. We can look at the porosity and density of these rocks, and that helps us interpret global data sets. For example, from the GRAIL mission, these are gravity data, and we need to know how porous or how dense these rocks are so we can interpret these maps correctly. We can look at the chemistry and the isotopes of either the entire rock or just part of the rock, or maybe just minerals, and that will help us understand how these minerals form, how these rocks forms, and therefore how the entire moon formed and what the history of it was, and these processes that go on onto the surface. By looking at the magnetic properties, we can also learn something about the interior and whether the moon had a solid and a liquid core that created a dynamo, because that will be recorded in magnetic minerals that we can study by looking at these rocks. So now you're going to say, great, so we've been there and we've done that. Why should we go back, right? So have we really learned everything that we possibly can learn, right? So if we look at a picture of the National Mall, Carrie, this for you, the Smithsonian right there, right? This is the Apollo 11 field site, and they explored a couple hundred meters, right? And so this is overlaid here on the National Mall, the area that they would have explored. So if you are going to be one of these astronauts and you explore this area of the National Mall, and then you come to Jersey or here and you tell me, guess what? I explored Washington. I'm going to say you're lying or you're full of crap. I didn't say it. Right? And so, okay, the moon is a little bit less complicated than Earth, right? And so if we look at the moon here, with the Apollo missions, and this is the United States overlaid on top of it, and I'm going to give you 6 missions. And you happen to land 4 of them in the United States and 2 of them in Canada. You get to collect 382 kilograms of rocks, and then you will tell me how the North American continent formed, or Earth, right? If I'm going to ask you that question, everybody in this room would be really hard-pressed to tell me how this actually worked, right? Because you were missing really, really cool places on Earth, like, I don't know, Australia, or the Saharan Desert, or Antarctica, right? All these cool things you would not have picked up in your rock collection. And just like that, we can't really say that we explored the entity of the moon. In addition to that, now that we have these global remote sensing maps and we can look at the distribution of particular elements on the surface, we realize that here's the near side. So that's the side that we always see where all the Apollo samples come from, this area right here. This is the far side, right? It's not the dark side, just making that clear. Far side that we never see. So this is where all the Apollo samples come from. And you can see it's highly enriched in iron, right? Well, maybe this could be a coincidence. So if we look at a different element, let's say titanium, also the Apollo areas are highly, highly enriched in that element. All right, well, another element, thorium, right? Radioactive, highly enriched in this area where all the Apollo samples come from, right? So geologically, super interesting, because we have no freaking clue how this happened to come there and why this all is there, right? but it's not representative for the rest of the moon because you can see the rest of the moon is very, very different, right? So if I gave you those 6 missions and you happen to land them in the Yellowstone National Park, geologically extremely interesting, supervolcano, hydrothermal activity, geysers, great. Not representative for the rest of the United States, right? So just like that, the Apollo samples are not representative for all of the moon. So if we only look at Apollo, we're going to miss a lot of stuff that's going on the moon otherwise. So that means we need more samples, clearly, right? Samples that come from random places, different places on the moon, different from Apollo and the lunar missions, right? Where do we get them from? Let's just go back. That clearly didn't happen in the last couple of decades. Hopefully this will happen in the future. What are we going to do in the meantime? We're going to get rocks in the form of meteorites, right? We all know meteorites come from the surface or the interior where a big impact happened and that blew off a little piece or a bigger piece into space, traveled, got captured by Earth gravity, and then survived the entrance into our atmosphere, went through as a meteor, and then eventually landed on the surface and got collected as a meteorite. So where do we find these meteorites? Where do they fall, right? And here again is another nice image of our planet. And don't get me wrong, I really like our planet. But if you were a planetary scientist who studies meteorites, this planet is not nice, right? It's covered in oceans, lots of oceans. 73% of the surface is covered. And meteorites fall randomly distributed. And that means 73% of the meteorites that we could study end up in the oceans and are gone. Now, if a meteorite falls, let's say in the United States somewhere, at night, and we don't see it, and it lands in a forest or a field, and nobody noticed it, what's going to happen to it? It's going to get rained on, it's going to get winded on, maybe a cow steps on it, I don't know, right? Over time, it's just going to weather away, turns into soil, and is lost for science, right? So our best places to find meteorites are places where the climate doesn't change much, where there's not much weathering going on. And those places on Earth we can find as deserts. Now we have 2 types of deserts on Earth. We have hot deserts, like Sahara or Northwest Africa, and then we have cold deserts. And this is Antarctica, which is actually one big cold desert. It actually turns out to be the driest place on Earth, surprisingly, right? And this is a nice view. You can see Chile here, there's Africa, Australia, New Zealand, right? Kind of a very different worldview from what we're normally used to. Antarctica is a continent, and this actually becomes important. And so it's covered with kilometers of ice. So if a meteorite falls in Antarctica, it gets frozen into the ice shield, into the blue ice, and therefore gets preserved in its pristine condition. And we all know that ice flows really, really slowly, but it flows. And so it flows from high places, like the top of Antarctica, the ice plateau, towards lower places, like the coast. And when the ice flows and it encounters an obstacle, so here are our mountains from the continent that come into play, if it flows against this, it's going to stall, right? It can't obviously push the mountain out of the way. And so the winds are so dry in Antarctica, they just simply ablate the ice away. They're just taking it away. It's not really melting. It's just ablating it away. So over time, the ice is going to push up a little bit. And so all the meteorites that got frozen over time and are in here and get transported like a conveyor belt, they slowly rise to the surface and all accumulate sort of like right here. And then all you got to do is go and recover those meteorites. No big deal, right? So NASA and Case Western University decided that this is a great idea, and every year they're going to send out 8 people to Antarctica to recover these meteorites. And the field team for this season, for 1920, they just left a couple of days ago, right after Thanksgiving. And so right now they're in Christchurch. I think, are they still in Christchurch? Yes, they're still in Christchurch, waiting to get deployed to Antarctica to start their big adventure. And so here you can see a picture of the previous seasons. You can see really how the ice flows around these mountains here. And so this would be, for example, an area where you might find something. If this ice is really young, your chances are kind of low. It, doesn't have enough time to accumulate meteorites. So you want to find these really, really, really old ice fields. And in 2017, I got lucky and got selected as part of the field team. And Dr. Barbara Cohen was actually my tent mate and showed me the the way of Antarctica, basically. And oops. And when they deploy you onto the ice plateau into the deep field, this is what it looks like. Here are the tents you're living in, and then you're stuck there for 6-ish weeks. No showers, just in case you guys had that question, right? You're living in here, that's it. And then you get to go and recover these beautiful, beautiful space rocks. And here's what it looks like when there's one in the blue ice, and you can see the rounded corners here. This happens when it tumbles through the atmosphere and sort of melts. That's why it has this black crust here, what we call a fusion crust, just the melted exterior. You can see me here in the field, completely bundled up because it is freaking cold. And here is one of the meteorites, so I'll get numbers. And then we have tools to pick them up. The really cool part is that last year's field season, they found new lunar meteorites on their field site. So they went to the Dominion Range, and you can see here, this is a picture that they sent me in the back of all 8 of them. And here, also not only searched on the blue ice, they also search in the moraines. And sometimes it's kind of, it's really tricky to sometimes see these meteorites, but you can see the black fusion crust, a little cracked here, and here you can see part of the interior and how it looks a little different. They picked it up. You can see it's kind of black on the inside, right? And I told you before we had these lunar basalts, and they were black just like Hawaiian rocks. And so this also has these clastic fragments in there. So this is probably a basaltic breccia. Just got classified by Dr. Carrie Corrigan, who's also here. Carrie, that was you, right? Yep, there we go. Thank you. And so Ryan and I requested a piece of this so we could study it. And so I'm going to show you the very, very first data we literally just produced. And so I'm going to show you an X-ray computer tomography image or movie. And so we had a little piece of the rock in the CT scanner. And what you're going to see is basically a movie of the slices we're going to go through, and that helps us to look into the inside of the rock, right? And so you're going to see a grayscale map, and everything that's kind of bright means it has heavy elements like iron or nickel or titanium in it, and everything that's kind of dark has more lighter elements in it like silica and magnesium and aluminum. All right, let's see if this works. Yes. All right, so here's the back. So here's part of the rock. You can start seeing it slicing through. Here's a melt vein. So this is part of the rock that got melted. You can see the black spots. These are vesicles. They're empty. You can see some big mineral grains. There's a big, big clast here. We think that's maybe recrystallized impact melt or maybe a basalt piece. You can see lots and lots of different mineral fragments. They're probably pyroxenes, maybe some olivines. The dark areas here, there's a big one. That's probably a piece of anorthosite. So by looking at this, lots of cracks, right? Very fractured. This helps us to see what the rock looks on the inside. There's some zoning going on here. And so we can make a good choice of where we want to cut the rock to expose the inside. All right, it's almost vanishing. Okay, so this one is a movie. Now we can use this data and make a 3D rendering, like a 3D image of this. And this is what this is. So here you can see it's rotating. You can see some fractures. And now it's going to stop. And now you can see the movie going, the slices going through a little bit faster this time. So now we can orient the rock and then see exactly where we want to cut it to get a representative area. We can also use this data and make everything vanish except for something that sort of has the same density. And that's what's going to happen now because we really wanted to see where this melt vein goes through. And so here you can see, everything else is invisible, how the geometry of the melt vein goes through this rock. Right? And now we can say, this is really cool, we're going to cut it right here, or maybe we want to cut it right here. And so we just got the data. And so hopefully in the next couple of months or so to come, we can also start getting chemical analysis on it. If there are really cool clasts in there, we can cut it so that we expose the surface of these little rocklets that are in here, where we can then get into more sciencey detail of like how we want to study this. Okay, so these meteorites are really important because they expand our view of the crust and of the moon beyond what we have with Apollo. And this is Allen Hills. It's another Antarctic meteorite that was found in Allen Hills in 1981. And this was the first meteorite that was recognized as coming from the moon. And again, the Apollo samples helped us to recognize that there are meteorites from the moon and what they might look like. And that's how we, or not me specifically, but other people were like, oh, this might be a rock from the moon, right? To date, we have about 148 lunar meteorites. They are comprised of about 400 stones. And that means when you have a meteorite that goes through the atmosphere, it oftentimes breaks up into little pieces, and they all fall onto the surface, and then we pick them all up. And then we think there are 4 or 5 different meteorites or different stones, but in reality, they all come from the same. So they're all paired, as we call a pairing. So we have about 400 stones, but they turn out to only represent about 150 different meteorites. And so on average, they come from random places on the moon. And so a lot of these are very different from the Apollo samples that we brought back. So by studying these, we can learn about processes that happen on the moon that are not represented in the Apollo collection. Oh, and just so you know, the world collection of meteorites overall is about, I don't know, 62,000-ish, and only 148 of those are lunar, so really, really rare. Okay, so I'm just going to quickly show you some highlights of cool new things we found. And so here is a new rock type that we discovered that actually Dr. Alan Treman and I discovered when I was a postdoc here. Super exciting. This is a thin section image, so you're looking through a microscope basically, and you can see all these pink spinel grains here. And at the same time, with remote sensing, they found a new lithology, rock type, and it turned out to be basically the same thing. And so here you can see the spectra from the spacecraft. And this line here in black is a spinel grain from Earth. And you can see that they have the same absorption bands. And there's these absorption bands we use to identify what kind of minerals or what specific rock types we have on the lunar surface. And so they presented this at the same time as we presented it, and we all got super excited at the conference and decided to collaborate and figure out how this rock type formed. And so here's what we think happened and why this is important. What we think happened is that we had really, really, really hot melt that was very magnesium rich from the interior of the moon that brought up through the crust, where now you have hot melt and cold crust, and so it interacts and starts melting it a little bit. And this is where you form all these beautiful little pink spinels, right? And originally we thought this could only happen in these really interesting, geologically interesting areas, because previously we thought you needed to have an energy source like radioactive elements that produce heat to melt the interior, to make this magmatism going on, to produce these pink spinels. Now with remote sensing, it turns out that they actually happen to be everywhere. And that means that this magnesium-rich, really hot melt was probably a global magmatic event and was not just located here. So that means that these radioactive elements are not the driver. They didn't make the melt, but it happened through some kind of different process. And when the melt came to the surface or so, it got contaminated by this region. We still don't quite know how this region works, by the way. Just so you know, super interesting active field of research. We also found the youngest lunar basalt in a meteorite. And that will help us to understand how long the moon was actually active with volcanoes. And now we dated this, and it turns out this is about 2.8 billion years old. And so we now know that the moon was active until 2.8 billion years ago. So that's super exciting. And that means that we can learn about geological processes, or there's a diversity on the moon that is just not represented through the Apollo collection. And this is the last really cool thing. We also found meteorites on the moon that are not from the moon. Right? So we found pieces of asteroids and maybe comets on the moon that got preserved in the lunar surface in the regolith that then got brought to us as meteorites. So we found a meteorite inside a meteorite. We also find these meteorite pieces, these exolunar pieces, in Apollo samples. So not just in meteorites, but also in Apollo samples. And that just means, as I said before, the surface of the moon is this archive that preserved the solar system climate. All this stuff was flying around early on that, not only impacted the moon, but probably also impacted the Earth. And so by studying these bits of pieces that don't come from the moon, we can maybe learn something about where the water came on Earth, or maybe even where life came from. I don't know. Right? It's really interesting and really important to study these pieces so that we can learn what type of materials were available while the Earth-Moon system formed. So bringing ANGSA back, this is the program that connects our past from Apollo, which is the back moon here, and our future, which is Artemis, and here's the today's moon with the Artemis symbol laid over, and Artemis is a sister of Apollo. And then ANGSA, which connects both, going somewhere maybe to the South Pole, is really important. Not only that the Apollo samples helped us and will help us understand how to collect samples from the South Pole region with Artemis, but we also need Artemis to maybe help ground truth lunar meteorites, because the stuff that we bring back from Artemis will most likely be more representative for the lunar meteorites than the Apollo. So most importantly, to remember from everything I just told you, number one, the moon is really, really cool. Number two, women scientists are awesome. And number three, lunar geology is really complex, and we really don't know everything about the moon yet. There's so much. We don't know so many questions we haven't even realized to ask. There's so many processes that we might have not even discovered yet, because we're still discovering new things, right? And so there's this critical need to study more lunar samples, either as return samples from Artemis or samples we haven't opened yet from Apollo, and of course also meteorites. So there's lots more to do. So you all should come back and become lunar scientists and have a second career, or a first career, or change your field, whatever you're doing right now, and become lunar scientists. And yeah, so with that, I want to thank you for your attention. And before we stop, in lieu of asking questions, you could instead, if I can open this, Ryan. Oh, there we go. I brought you something very special. You could touch the moon. We brought you a touchstone. Okay, so you can come up and actually touch the moon. I'm not kidding. So, the end.
Well, as much as we'd love to not have you on the spot to answer questions, we're going to do it anyway.
Oh, and Ryan is going to answer all my questions. Just so
okay,
you know.
Ryan, come on down. So, all right, anybody, any questions?
You touch this without my permission. I'm going to tackle you. Just no. Yes, you may touch.
Well, back in December 1972, when I was watching the Apollo 17 EVAs and they said orange soil, I almost jumped out of my chair.
Oh man, I'm so
So
jealous.
can you tell us what the orange soil is and its composition?
Ryan! So the orange soil are volcanic glass beads that were brought up to the surface from basically volcanic activities. And I do not know what the composition is because I don't study those.
Iron and titanium rich.
Iron and titanium rich.
This is what you showed us on the graph.
The iron, yes, I showed you, and the titanium. That's very right, exactly. And so, as you can see, you know, that's where the Apollo samples come from. So they're all kind of like contaminated. They're just not representative. They're cool, they're awesome, and I love them. They also really like meteorites. Is Cecilia here? Don't tell Cecilia I said this. That's a very good question. So the question was whether the ice transport system, the kind of like the conveyor belt that works in Antarctica, also works in Greenland. So we find meteorites in Antarctica because the ice has been around for a really, really long time and had a really long time to collect these meteorites. So the ice is really, really old when it flows. And as you have seen, the continent is really big. Greenland is a lot smaller, and so the ice is a lot younger. So you could potentially find meteorites there. Not sure how likely this is. Carrie can answer that question better.
They did it
So no.
I think it was too warm.
There's no barrier in Greenland.
There you
They
go.
go right off the ice into the ocean.
Into icebergs, and then they drop into the ocean. So if you're a meteorite, you don't land there.
We don't have a choice.
If you had a choice, don't go there. Also, you know, South Pole has penguins versus. Yeah, you don't mess with the polar bears.
Do we have any teams currently searching the ocean floors for meteorites?
So the problem with that is the ocean is really deep, right? And once the meteorite lands in there, it's sort of contaminated and will fall apart and weather rather quickly. So we do have some people who look in water and like scoop some stuff up, and they find little spherules and droplets. And we have somebody at JC who actually does look at these, and they're really, really cool when we look at under the SAM and see these little chondrules and chondrule-like meteorite parts. So yes and no.
Every image and discussion I've heard about collection of the meteorites in Antarctica involves picking them up off the surface, but it seems that you're waiting for that weathering of the evaporation of the ice. Have you ever dragged a sonar looking for things just below the surface to try to dig down to them?
That's a really good question. So the British just deployed a team out, also just left to a different part of Antarctica, and they're going to drag these massive plates behind their skidoos, and they're trying to find iron meteorites, kind of like a metal detector thing. So they're going to test this out this field season. Well, they tested it out last field season. Now they're going to go back and really try to see if they find something below the ice, because one of the hypotheses is we don't find a lot of iron meteorites in Antarctica, and so when the sun shines on them, they might get kind of warm and sink back into the ice, and so maybe they're just a couple meters under the ice. Maybe there's a lot, maybe there's not. We don't know. So they're going to try and see what they actually can find. So fingers crossed.
What is your criteria for trying to determine if a meteorite is from the moon?
Oh, very good question. So the good thing is that we actually had missions that went to the moon and brought samples back. So if we have a meteorite, we can compositionally directly compare it. And there are different methods. We can look at isotopes, which for the moon is not that helpful because it has the same isotopic signature than Earth. But we can look at mineral elemental ratios. So iron and manganese ratio is very different for minerals that crystallized on the moon than for minerals that crystallized on Earth. So we have trend lines, and we call them chemical fingerprints. So we simply chemically analyze these mineral grains, and then we plot them. And if they don't fall on the trend line for Earth, but fall on the trend line for the moon, we know, yay, moon. If they fall on the trend line for Mars, which is again very different, yay, Mars. Mars also has a very different oxygen isotope signature, so have very primitive asteroidal materials. And so we can use different geochemical criteria to pinpoint down where these meteorites come from. We can do this because we have Apollo to compare them to, and we have rovers on Mars to compare them to. And we have some data, reflected light from some asteroids, that we can then compare the reflected light from meteorites in a lab and see if it's sort of similar. And then we can say maybe it comes from an asteroid. If it doesn't fall on any of these and any known oxygen isotope ratio plots, anybody's guess. Maybe Venus, I don't know, right? Maybe, I don't know, Mercury. Very unlikely, but we just then simply don't know where it's from or what it is. Yeah.
Looking at it from a geological standpoint of view, what part of the moon would you like to see us go back to collect moon rocks, and why?
Backside, the far side that we don't see. And then I would personally like to go to the Moscoviense Basin because there's a lot of different things going on at the same time. We have pure anorthosites that we think come from fairly deep in the crust that were brought back to the surface. We have basalt there. We have these weird, what we call lunar swirls. There's something going on the surface that we don't quite understand, maybe with space weathering. We have these pink spinel outcrops in there. It'd be really cool to get an actual fresh sample and compare it to what we have in the meteorite. So there's a lot going on in the Moscoviense crater. So I personally would like to go there. Not sure anybody's going to listen to me, but yeah, personally, that.